reshare my screen for the next presentation, which is Brendan of Rogers from the Boreal Climate Institute.
All right. Thank you, everyone. Hope you had a good lunch. So I'm going to follow on the theme that Sophie brought up to talk about wildfires and carbon and some monitoring. And just to note that I was meant to do this with my partner in crime, Kyle Arndt, for Global Gulf Tiber Research Center. He got stuck in Vancouver. So I'm going to try to do his slides justice, but he would have done better. He's really an expert on the monitoring side, the flux network, the eddy covariance towers that were talked about earlier today. So I'm from Massachusetts, traditional land of Wampanoag people, part of the Permafrost Pathways projects doing science and policy around permafrost thaw. Okay, so we probably all know that temperatures are warming rapidly in northern regions. This spinning globe on the left, which I really like, is a representation of that, or orbiting rates are shown as topography. So this big red knots you see in the Arctic are representative of how quickly high latitudes are warming compared to the rest of the planet, about 2 to 4 times. And one of the reasons that we care about that is because of the carbon we've been talking about here today. So carbon in the tundra, carbon in the boreal ecosystems, carbon in permafrost, and shown on the right is a photo of a slab of permafrost. It's a lot of carbon, and a lot of numbers are being thrown around, but roughly 1.6 trillion tons of carbon in permafrost. It's about 3 times all that's been emitted by humans today. It's about 3 times all the carbon around biomass and Rourke's forest. It's a lot. We're not expecting all of that to be emitted, but even if a fraction is emitted, that obviously is a significant number. Also important to point out that we are seeing more plants, more greening, more photosynthesis of CO2 in the summertime, but we're also seeing more respiration and in the summer season and outside summer seasons all year round. And disturbances, wildfire, permafrost thaw, they're releasing that carbon back to moisture. Fire is a big part of that, especially here in Northwest Territories. You all know this. You lived through it in a way that I have not and might never will in Northwest Territories. It's a big part of the carbon balance. So these slides are just going to be looking at really Canada and Alaska, but the next that we'll go into Northwest Territories specifically. So this is looking at some work we did a few years ago, thinking about, okay, what is the net balance of CO2 from fires? So we incorporated not only what's going into the atmosphere when they burn, but also what's getting regrown when vegetation regrow after fire, which is why it's negative some years. And it was sort of project that out to the future with intensifying fire regimes. And one of the numbers we get from this analysis is that in Canada, we expect about 1 to 8 gigatons or billion tons of CO2 to come out in net from fires because of warming and climate change. And that's about 1 to 14 years of emissions from all of the sectors in Canada combined. So it's significant. But this is probably conservative. In some sense, we don't include methane and other gases in this analysis, and we also didn't include interactions with permafrost. And this was done, as you can tell, before 2023, so we are getting surprises. I think in some ways, like I would just say from the scientific community, 2023 kind of reset our expectations of what's possible. And so, for instance, on the carbon side, the emissions span about 1.5 to 2.5 gigatons CO2. So if I were to remake that graph on the left, I have to basically double the y-axis just to capture what happened at 2023. This is also happening in Northwest Territories, and there's some really great maps on the wall and the pamphlets on the table. You can see that one I show here on the left is similar. It's looking at fire across the territories. By decade, there's a lot of red and orange, meaning you've seen a lot of fires in recent years. Top right, you can see a time series of that since the governors were taking records, and this sort of upward trend, similar to other areas across the Arctic Boreal region. The biggest years in recent memory, of course, being 2014, 2023. And then on the bottom, looking, it's it's only the last 20 or so years, but the carbon emissions coming from those wildfires. And this one point of comparison, the anthropogenic emissions in NWT are comparatively small. So, like, for example, the 2023 emissions were about 270 times that from all the sectors at NWT combined. So it's hard to think about carbon here without thinking about fire. And then this right now, this is our best guess of what this all looks like. Serpent-pole. So this is Alaska, Canada, Russia, Scandinavia. We're using a modeling approach to look at the emissions we expect from gradual permafrost thaw, from abrupt permafrost thaw, from fire combustion, post-fire thaw, out to about mid-century. And it's a lot. I guess it's important to note that the increasing uptake we're seeing from plants that is generally captured in the models. This was mentioned this morning. Was not captured are a lot of these lost pathways, and so these are essentially unaccounted for. And they add up to about a 10 to 20% reduction in allowable emissions to stay within like a 2 degrees Celsius target. So these are important numbers that need to be considered for policy. Okay, here's where I would pass it off to Kyle. So I'm going to try to channel my ear, Kyle, and move on to monitoring. So I think that all underscores how important it is to be monitoring what's happening on the ground as climate is changing, as things are happening, to understand the carbon balance and if you think about actual solutions. So we've been focused on this as part of our Protocols Pathways project. Those eddy covariance or flux towers that were mentioned earlier, you've been supporting them. You've been trying to synthesize the data from them. It's really important to think about capturing both CO2 and methane in all year round because we know emissions and fluxes be happening. So this map shows the current active towers in Canada, red for CO2 and methane, green for CO2. I think the legend got a little bit messed up, and then yellow are sites that our project is supporting. Circle is all year round, and triangle is only in the summer. The point is that we're thinking about this from a point of view of like how we put towers out there to understand the net balance. What ecosystems on climate area would you mean to cover? The map in the background is kind of what we use, and so it's this representatives analysis that I think Alan mentioned about looking at climate and vegetation and soils and what ecosystem do we have information on and what do we not. And the picture actually looks pretty good for summer CO2 there, right? Like the good well cover regions are sort of in the yellow to red colors. But when we look at, for example, all year round CO2 and methane, you can see that there are definitely still quite a number of gaps, including the southern Boreal and parts of Boreal, etc. So this is something we've been focused on to try to cover these. So we try to cover these different environments. So here are some sites. I think they're all managed by both Alan Humphreys and Oliver Sonnentag, who are here today. These are all in the Northwest Territories, including Scotty Creek, which burned down in a great late season fire a couple of years ago. But just to sort of highlight the different kind of environments that we're trying to capture the CO2 and methane data from. And then here's a zoom into Northwest Territories, the sites that are active here, looking at both CO2 and methane, but the map is showing summer coverage. And just some notes from Kyle in terms of thinking about, okay, if we were to expand the coverage of sites, what would we be looking for? So increased year-round coverage is important. Dryland representation, so likely having low flux magnitudes, but really important to understand. We try to take all these data together and look at the net flux across larger areas. And maybe prioritize its southern border and wetland sites as well, and comparatively tundra BC relatively low coverage. This is an example of one of the things we do with those data. So this is a paper that just came out maybe a couple weeks ago. We took at all the CO2 data that we had, not only the active sites, but the sites that were emissioned. We couple that together with like sensing and a lot of different spatial data sets and machine learning and try to understand the net balance of the whole region. Here it's all Arctic and Boreal biomes, and this is coupling both the sort of exchange, as towers are measuring, also the direct emissions from fire that I was talking about early. So all those like very dark red splotches, those are where fires have happened during this 20-year period. And a couple take-home notes from this. One, I guess, good piece of news is that the Boreal region, all that blue, so the Boreal region is still acting as a very important carbon sink. The permafrost region, which is sort of a subset of this, I'm not showing it on the map, I apologize, but that's about neutral, the CO2, if you add on fires. And it does look like the tundra has, according to this method, become a small annual CO2 source, which is important to note because that's different than how the tundra has acted historically as a parts. This is the final slide, zooming into Canada. And a lot of numbers here. I guess I would just draw your attention. One thing, so the sort of without fire and with fire numbers, negative numbers are the ecosystems drawing CO2 in and sort of sequestering carbon, and positive numbers are coming out. So this is all saying that Canada still is acting as a carbon sink, which is good, even with fire included. Now, I should note we did in this, it's really complicated, right? We didn't include aquatic, we didn't include the transfer of carbon to the ocean in this, so it's not a fully closed budget. But nonetheless, However, for Northwest Territories, when you include fire, it goes from a sink in black, so -70, to a carbon source at 8. And, again, the anthropogenic emissions are relatively small here, so any change in the natural emissions is going to look big, and it does. So with fire, natural systems emit about 10 times that at human emissions in Northwest Territories. So, again, it's a bit hard to think about carbon balance in this region without thinking about fires and not ages. Okay, I think that's all I have. Sort of in time.